Hello again, everyone. So, now we have the most generalized version of the modular multiplication problem that we can get. We want to show that if A1 is congruent to A2 mod M and B1 is congruent to B2 mod M, the first thing we want to show is that A1 times B1 is congruent to A2 times B1 mod M. Part B asks us to show that A2 times B1 is congruent to A2 times B2 mod M. And then finally, the big part that we're working for, the massive part of the problem, is that we want to show that A1 times B1 is congruent to A2 times B2. Basically, that if I have two numbers that are congruent mod M, that those products will always be congruent mod M. So, as always, let's begin with some exploration of what we know. For instance, starting off the same way we did last time, we have that the difference of the two, A1 minus A2, is a multiple of M. So it's the same thing as M times some integer K. And again, if you're not sure, always refer to the old definitions. So, A is congruent to B mod M if and only if the difference between A and B is a multiple of M. Meaning it's in some sort of form like this, which is what we just did with A1 and A2. And we could do the same thing with B1 and B2. You have that B1 minus B2 is also a multiple of M, but times some other integer J. So now let's work on part A. Part A states to show that A1 times B1 is congruent to A2 times B1. So just looking at this, I have A1 and A2 on both sides of the congruency statement, and B1 is on both sides. So that means thinking ahead, if I can just show that those two values, the difference is somehow a multiple of M, then I've proven a congruency. And I think the easiest way to do that is to take the fact that A1 minus A2 is equal to MK, M times K. And this is like the same procedure we did last time. I'm going to multiply both sides of the equation by B1. And that becomes A1 times B1 minus A2 times B1 is equal to M times KB1. Now we know that B1 is an integer, and we know that K is an integer. So, K times B1 is also an integer, and since it's being multiplied by M, it must be a multiple of M. So, we get our congruency that A1 times B1 is congruent to A2 times B1 mod M. Nothing tricky so far. This is basically just like the last problem, except instead of a 6, it's an M. But the same logic still applies. Now, part B. Show that A2 times B1 is the same as A2 times B2. Now, since I have a B1 and a B2, I have the intuition I should probably use this equation right there. because I can repeat a similar procedure what I did last time by multiplying both sides by A2. So let's write that out. B1 minus B2 is equal to M times J. And let's multiply both sides of the equation by A2. And what that becomes is we distribute the A2 and get that B1 times A2. Or I guess I should write it in the same form that our problem's asking. A2 times B1 minus A2 times B2 is equal to M. I'm just using the associative property of multiplication to rewrite the parentheses so that we have J times A2. And like we have done in the past, we have basically proven, we have proven that since the difference of A2 B1 minus A2 times B2 is a multiple of M, then we have our congruency. So we have shown that A2 times B1 is congruent to A2 times B2 mod M. And that's it for part B. So far, everything looks very similar to the previous proofs we have done. So, part C. Show that A1 times B1 is congruent to A2 times B2. Well, how about let's use some of the things we have established already. I know we have shown that, like, for instance, here, I'll write part C. We have shown that A1 times B1 minus A2 times B1 is equal to M times K B1. Oof. K times B1. And I'm going to use the information from part B, namely that we have A2 times B1 minus A2 times B2, and that's equal to M times J times A2. I have those things which have been proven so far. Now, I have two equations, and I can see, just looking at what I have, that we have negative A2B1 on the first equation and a positive A2B1 on the second equation. And in math, we like when stuff starts to cancel each other out. So if I add these two equations together, we might come across something interesting. So by adding these two equations together, the left-hand side, I get A1 times B1. Then plus this A2 plus A2B1 minus A2B1, and then minus A2B2. That is equal to, now I can't really do much right now, so I'm just going to leave it as M times KB1 plus M times J A2. But now what I can clearly see is that if I group these up together, we have a2b1 minus a2b1. And anything subtracted with itself becomes a 0. So I have a1 b1 plus 0 minus a2 b2. Now, on the right-hand side, I notice that both terms have a factor of m. They have an m over here and an m over here. So what I could do is factor out that m. So I'm going to factor out the m, and what I'm left with is k times b1 plus j times a2. Then I can simplify even further. This 0 just goes away. We have that a1 b1 minus a2 b2 is the same as m times k b1 plus j times a2. Now, where does that get me? Well, looking at the right-hand side, I have m times some value. That value is made up of the product of two integers, which would be an integer, and another product of two values, which would be another product of two integers, which would be another integer. And if I add two integers together, that would get me an integer. This is sort of common sense, but it can be a little confusing when we're just working with unknowns and variables and letters. But just think about it. If I multiply two whole numbers together, k and b1, I get another whole number back. As same with j times a2. Two whole numbers multiplied together gets you another whole number. And if you add two whole numbers together, you get a whole number. So what this is an integer times m. And that's equal to a1 b1 minus a2 b2. And since it's an integer times m, that means it's a multiple of m. And if it's a multiple of m, that means by the definition of congruence, of modular congruence, we have that the difference of these is a multiple of m. So a1 b1 is congruent to a2 b2 under mod m. Thus proving our modular multiplication theorem. So this has established that if we have four integers, a1, a2, b1, b2, and if a1 is congruent to a2 mod m, and if b1 is congruent to b2 mod m, then the multiplication of those integers, the product, is also congruent mod m. No matter what those values are, as long as we have these previous two congruences, we will always get a third congruence with their products. So, in the next videos, we will explore exactly how to work with this information and how it can make problem solving very easy and make some complicated problems much more simplified.